estimate the time required to convert a k-bit integer n to its representation in base b, where b might be very large. The same algorithm which we used for conversion to binary number system can be applicable here also. Let L be the number of bits of b, and we know that this will be equal to big O of log b. Also, we are given that k is the number of bits of n, so that will be equal to big O of log n. To convert n to base b representation, we will be dividing n by b, and then we will be dividing the quotient in the first division by b, and so on. This process will be repeated until we get the quotient equal to 0. We know that the number of bit operations in each division will be less than or equal to number of bit operations in the first division, because in the first division the largest numbers are involved. That is because we are dividing n by b in the first division, whereas in the second division we will be dividing the quotient in the first division by b. So the numbers involved will be smaller in the second division when compared to the first division. So the number of bit operations in each division will be less than or equal to number of bit operations in the first division. And in the first division, since we are dividing n by b, the number of bit operations required will be less than or equal to k into L, since k is the number of bits of n and L is the number of bits of b. So we can write this as, that is, the number of bit operations in each division can be expressed as big O of KL using the definition of big O notation. Also, the number of divisions required will be equal to the number of digits of n in its base b representation. So that will be equal to big O of log n. Since k is the number of bits of n, it is equal to big O of log n. So we have big O of k is equal to big O of log n. But we know that if f is equal to big O of g, it means that f is less than or equal to c into g. And so if h is equal to big O of g, that means that it is less than or equal to c into, say, some other constant d into g. So h is less than or equal to a constant multiple of g, which will imply that h is equal to big O of g itself. What does that mean? Big O of g is equal to big O of g. So we can write big O of log n as big O of log n itself. And we know that the number of digits of n in its base b representation can be expressed as big O of log n by log b, and that is equal to big O of log n by big O of log b, and that can be expressed as big of log n by big of log b, using the property we just proved. And this is equal to big of k, since k is big of log n, and since big of log b is equal to L, the denominator will be equal to big of L. So we can express this as big of k by L. So the number of divisions required for our algorithm is equal to big of k by L, and the number of bit operations required in each step is equal to big of k into L. So the total number of bit operations required will be equal to the product of number of divisions required, that is big of k by L, into number of bit operations required in each division, that is big of k into L. So this will be equal to big of k by L into kl, and it will be equal to big of k square. Since k is the number of bits of n, big of k square can be expressed as big of log n into big of log n, and that can be expressed as big of log n into log n, which is big of log square n. And we know that big of a function is equal to big of the same function. So this is big of log square of n, and this is the answer we obtained in the previous example also. That is, this represents the number of bit operations required to convert n to binary system also.